joining, but we can slowly start. So welcome everyone for the second talk of the session. So the morning talk was on simulations and theory mostly, and now we will again move to something to do with data. So our next speaker is Professor Bhaswati Bhattacharyya of NCRA TIFR. Bhaswati is also a radio astronomer primarily, and her research interests are mostly on pulsars, and you will know what pulsars are and what the challenges are and how they connect to our HPC applications in the talk. So again, I will request everyone to mute themselves during the talk. And yeah, Bhaswati, you can start.
Yes. Hello, everybody. Today I will be talking about pulsar searches and relevance of having higher computing facilities, especially why we need high performance computing for pulsar searches. And this is a field maybe some of you already know, and I will also talk about introductory stuff so that people who are getting introduced to this field are also getting the feel of the subject. So any place, if you have any question, maybe I will have some pauses and then you can ask. Okay, so let us start with pulsar searches. So first of all, before I start on what are pulsars and why this talk is actually relevant, let us look at, so the thing that I will be presenting in this talk is a work from a large team. So these are the team members. So as you can see, the team members are both from India, and internationally there are also some members. And also we have quite a lot of students who are putting in hard work in the pulsar searches with the GMRT, which I will elaborate in part of the talk. Okay, so these are the pictures of the team members, and you may know some of them, or you can see which names where you can put in. Okay, now let us come to the plan of the talk. So this talk, we will introduce pulsars, but that will be a very brief introduction and mostly from observational point of view for the interest of time. And then we will talk about compute requirement for pulsar searches, some limitation that the ongoing surveys with the giant meter wave radio telescope and the other telescopes all over the world that are facing in discovering new pulsars. And then I will tell you about some results of blind and targeted surveys with the GMRT where I was involved, and then on the relevance of HPC in future pulsar searches. We'll conclude with that. Okay, so to start with the introduction to pulsars. So pulsars are timekeepers in the sky. You can think on that way. We all have, and our you can consider the second arm of your watch take a full round through in 1 second, and you get a tick in the clock in your clock which you have. Similarly, you get ticks in pulsar clock, which are pulses received from the pulsar. Okay, and the second definition of the second can be different for different pulsars. What I mean is different pulsars will have different pulse period, which is the separation between these two pulses. You can see my pointer. So separation between these two pulses are called pulse period. So each pulsar have its own characteristic pulse period. That means pulsar is rotating and the beam from the pulsar which is emitted like this is cutting your line of sight after a regular interval. Okay, so this is pulse period. So each pulsar have its characteristic pulse period. And if you look at a schematic diagram, so this will show, so you can consider pulsars as a very strongly magnetized neutron stars, and this axis is the magnetic axis. If you consider it to be a dipolar magnet, very strong dipolar magnet, and whose strength is much more than, maybe you can't see from here, maybe I can hide this. Yeah, sorry. Yeah, now you can see. So you can see that the magnetic field of the pulsar is really high. Such high magnetic field cannot be created in Earth. And so these can be used as natural laboratories where the behavior of matter can be studied in such higher magnetic field. And you can see that this is our line of sight, how it is cutting. This is the emission beam from the pulsar, and this is the axis around which the pulsar is rotating. So depending on the emission geometry of the pulsar, you will see different kind of pulse shapes recorded from the pulsar. Okay. So here, this is more clear. So you will record, what you will have is you will record the individual pulses from the pulsar, which is seen over here. And if you average all these pulses, since you know a characteristic period, which is the time difference between the arrival time of these pulses. So if you average all these pulses, then you will get something called the average profile, which is like this. Okay. And you can see that different pulsars have different average profile, characteristic average profile, which could be single, double, or multiple. Yeah. So pulsars will also have its own period. In addition to that, it will also have its own period derivative value. Okay. Which is P dot. That means, though I am saying the pulsars have constant, very precise period, these pulsars are slowing down very slowly. So it has its period derivative value, and if you plot period versus period derivative, generally you get this kind of plot where these blue points are for what we call normal pulsars having periodicity more than 30 milliseconds, and these green points are for the millisecond pulsars, which are very fast pulsars and are used for gravity test. Okay. So now, we now know that what are pulsars. Pulsar have its characteristic period, it has its characteristic period derivative value, and it also have another characteristic, this thing, which is called dispersion measure, which defines its position. So it is defined by where the pulsar is located and what is the medium between you and the pulsar, or the observatory and the pulsar, so to say, and we call it dispersion measure. So these three characteristics, one pulsar have: period, period derivative, and dispersion measure. I will define the dispersion measure and mathematically and show in follow-up slides. So now we know that these are the three intrinsic properties of the pulsars. Now, and these are you can consider as laboratories in the sky for us to study different how the matter behave in extreme conditions, such as extreme density, extreme magnetic field, and so on. And also we can use these precise pulses that are coming to us to determine the condition of that particular pulsar laboratory. Okay, so each laboratory will have little bit different condition. And we can also use this precision timing of the individual pulses or the average pulses from a pulsar to do see how the medium, that means medium through which the pulses are coming, are affecting the detection. That means collectively we can see how the time of arrival from a pulsar, from a collection of millisecond pulsar, and then we can try to detect the signature for gravitational wave. Also we can, which is this point, and then we can also probe the neutron star interior by looking at the regularity of the interval in which these pulses are coming, and also we can see we can probe the condition in which are generating these pulses by doing single pulse studies. So these things, if you are interested, you can go back and refer to the specified literature which are explaining all this. In this talk, I will not have the scope to reach tell more on these topics. So the point is, we know many things. We know that with pulsars, one can probe many disciplines, and one can know many things. And people have, over the years, from the discovery of pulsar in 1967 till now, people have done that. But till now, only 95% of the pulsars are known. That means whatever study people have done, researchers have done, are based on only on the 5% of the pulsars. And the population study is saying that 95% pulsars are not known. So we need surveys to reach out. And we need to know why these 95% pulsars are not known, to take a step so that we can know this. Okay, so this talk will tell you some of the reasons and probably some of the possible solutions. Okay, before that, just briefly, I have already talked about normal pulsars and millisecond pulsars. So these are basically distinguished by the period range in which they emit pulses. And then there are magnetars, rotating radio transients, intermittent pulsars, and also giant pulses. Here also I am not getting into details of all these things. References are there and you can read about all these disciplines. Now, coming back to the compute requirement of the pulsar surveys. Now, the pulsar survey data are recorded at very high time and frequency resolution. Okay, so time resolution is around microsecond and frequency resolution is around kilohertz. So, which leads to very large data volume. So, around 48 MB per second data volume. And depending on how long your observing session is, this can generate 1 TB or 2 TB of that order data volume recorded in each session, each epoch, we say, of observation. So you can understand, to record that much data, to store, and then the processing thing will come up. It requires a lot of computation power, right? So now I am going to how do we search for pulsars. Okay, so searching for pulsars, while searching for pulsars, we need to search in 3 dimensions. I have already told that pulsars for searching purpose, initially we will think of 3 parameters, 3 characteristics that pulsars have. One is it has characteristic dispersion delay, it has its own periodicity, and there is some change of periodicity if the pulsar is in binary orbit. Let me first define what is this dispersion delay. Okay, then I will come to rest of the parameters. So this dispersion delay is due to the dispersion measure value of a given pulsar. So each pulsar is located at a given place in the sky, and the medium between the pulsar and the observing, so you can say if you are observing from Earth, so the telescope is different. So your line of sight from pulsar, so when the pulsar signal is traversing through the ISM and coming to it's being recorded in the telescopes, it is traversing through a medium having some electron density. So this dispersion measure is nothing but the integrated line of sight column density. Okay, and as you know that the signal from the pulsar will be subject to this dispersion, right? Because low frequency signal will travel at a different speed and higher frequency signal will travel at another speed. Okay, so because of that, one needs to correct for this delay, which will happen between, say you are observing at a given observing frequency from 300 to 500 megahertz. So between these two ends and between what we call frequency channels, there will be defined dispersion delay. So during the analysis step, during the analysis, one needs to do correction for this dispersion delay. So this equation, this shows how do we correct for the dispersion delay. So as you see, so this delay is dependent on the dispersion measure of the particular pulsar. So once you know the dispersion measure of the particular pulsar, you can calculate the delay between adjacent frequency, when the signal will come between adjacent frequency channels, and then you can compensate for that. Okay, so while searching for pulsar, what we do is we will try different dispersion measure values. So these are different trial dispersion measure values, from very low to very high, because when we are searching blindly, or even for some of the targeted searches, we do not know the dispersion measure value of the target source. So in that case, you need to search for a wide enough dispersion measure value to compensate this effect. So first step for pulsar search is de-dispersion. Then what you do is, then you have, say, this upper panel is your signal recorded from the pulsar, where you cannot see the pulsed signal, right? Because it is hidden in the noise. Now, if you fold each and every individual pulses and stack together like this, then you will build up the signal above the noise. So this is called folding. Okay. So when we observe a known pulsar, then we perform these two steps. We disperse at a known DM dispersion measure value and do folding. Now, when you are going to the search for pulsar, you do not know the dispersion measure of that particular pulsar. So you need to search for that. A. B is you need to do search for the period of the pulsar. This difference between the consecutive pulses, time difference between the consecutive pulses. You need to search for that. Now, the point is why you need to search for that? Because you need to fold the data. Otherwise, if the pulsar is weak, you will not get to see the pulses. Okay, so you need to do periodicity search. Again, now some of the pulsars are in binaries. So that means they are rotating around another object. So if they are in binaries, your detected period will be function of the binary orbital phase at which you are observing, right? So your observed period will be Doppler shifting. Okay, so you need to correct for this motion. So that means effectively what will happen is you will have a period derivative, which is in addition to the pulsar's intrinsic period derivative that you saw in the BP dot diagram, it will introduce period derivative due to the motion in the binary, which we call acceleration. So you need to correct for this acceleration also. And in the course of my talk, I will also make the things complicated by adding another period derivative. So acceleration you can consider as searching in period derivative, and if you search for period double derivative, then we will call that jerk search. And each step if you introduce, so basic necessary steps are the dispersion, that means correction for dispersion delay and correction for intrinsic periodicity. So if a pulsar is very slow pulsar and it does not have any acceleration, then these two will be sufficient. Now, most of the millisecond pulsars have acceleration, so third step is required. The moment you introduce the third step, your compute need goes up a lot. And the moment you introduce another second derivative, which I call jerk in periodicity, your compute requirement again goes up. And also you can here, while searching in this 3-dimension, you can choose your grid size to be smaller or larger, and as you can see, smaller grid size and more number of trials will need more compute cost, but at that cost you may get some good discoveries which you are missing otherwise. Okay, so this is a view of pulsar search pipeline, which you may look at later. I will not get into the details of that, but just for reference, you may look at this. And this figure is being generated by Shubham, who is a PhD student and doing pulsar search extensively and have discovered a couple of pulsars. So you can see this raw data from the telescope is like this. And then we do some mitigation of radio frequency interference, which is a very big part, because otherwise your pulsar signal will be masked by the interference signals. And then you do de-dispersion, which I said at multiple trial DM, say DM1, 2 and all, you will do de-dispersion. And then after doing de-dispersion, you will search for, do like Fourier transform the time series to find out the periodicity. That is the way in which efficiently one can search for the periodicity, underlying periodicity of the pulsar. And then you do de-deadening to make the noise less, and do periodicity search, get the candidates, and then after looking at the candidates, like possible candidate pulsars, what you will do is with the period and DM, at that point you have the chosen period and DM where likely pulsars are. So these will be folded. Say you will have 10,000 candidates with folded with the period and DM predicted by this search pipeline. And from that, you may clean the candidate. That means take out even residual RFI which are present. And then, since the manual investigation is almost not possible, we will do machine learning, apply machine learning. That means train the machine to know which features in the data will tell you that it is pulsar like, and then we will have these candidates, and after that we will view those manually and see the pulses. Like here in this last plot, you see this pulse phase versus time, you are seeing the pulsar, and pulse phase versus frequency, you are seeing this dark line, which means that this is pulsar. Okay, good. So now coming to Pulsar Search as a computational problem, you have already seen that as you increase the number of DM, as you increase your observing bandwidth or the time of observation, your number of operations needed for doing Pulsar Search is increasing. And in addition to that, so this is the dispersions, like making the de-dispersion at different DMs. After that, the next step is the periodicity search, which will involve acceleration search. And depending on how many acceleration steps you are using, your compute need will increase by many fold. Okay, so we will of course need high performance computing. So there is no other way out. Okay, so now I am just giving you one idea of very basic pulsar search without doing very fancy things or getting into the parameter space, which are like very promising but needs more compute power. So we considering that we are using what we are using is 192 cores from NCRA HPC, and we are having around, so for 10 minutes, so one pointing is around 10 minutes if I consider. We need around 200 CPU hours for the basic minimum searching, which will lead to like it will take around 10 hours in the HPC to process. So you can see that with CPU doing the this thing, so having pulsar searches in individual CPUs is not at all a possible job. Okay, so we will need to go for high performance computing, and what will be your target parameter space will be decided by what is the compute power available to you. Okay, so now I will also want to point towards this web page where it is possible for students and others who want to get into Pulsar Search. So you can look at the data from different from the GPT, which is Greenback Radio Telescope, and there is this Pulsar Search collaboratory which runs, and it is possible for students to get involved, and there are tutorials for, and also helps and mentorships for training students in this. So you may think of this. Okay, now let me come to, now you can say, okay, fine, you are doing Pulsar Search, it is a compute intensive job, you are doing this with different HPCs. Now, why we need more HPC, and why, first of all, this 95% pulsars are not known, since you know what is the problem. So before going to that, you can see that, so in this plot, you can see the milestones in pulsar discovery, most of this, but maybe some are missed. So like the most important is, like, say, discovery of double pulsar system, or fastest millisecond pulsar system, first discovery of rotating radio transient, which are pulsar light, and many all. I will not name all of this. So you can see that number of pulsars per year is increasing. So this red curve shows how the number of pulsars is increasing per year, and this green curve shows how the number of millisecond pulsars is increasing per year. And you can see that after some time, say, millisecond pulsars were discovered later than normal pulsars. You may ask why. The answer is most probably the compute power was not sufficient. And then even when it was discovered, you can see that normal pulsar discovery is at a higher rate than millisecond pulsar. Question is why? Maybe millisecond pulsars, maybe not. I would say yes, millisecond pulsars are less luminous than normal pulsars. So it is more difficult to find, so you need higher sensitivity of the telescope to find the millisecond pulsars. That is one reason. The next reason is the compute cost. And as I have said, to find the millisecond pulsars, you need, because most of these are in binaries, you need compute-intensive acceleration search, and which with time people are catching up. So, these being the reason, and also there are some surveys like Fermi-directed surveys, I will try to touch upon it briefly, which increase the discovery rate of millisecond pulsars in some time. So, what are the limiting factors in pulsar surveys? As I have said, one is sensitivity of the survey. So how can one overcome that? By building larger and larger telescope. But mechanically building larger telescope after a point is not possible. So large, like array of many small number of telescope is the answer to that. So basically one has to increase the sensitivity of the survey. So that is one point. Next thing is the compute power. So if one has higher compute power, then one will be able to discover more pulsars. Why? That will be more clear in the course of the talk, because we will be going to the parameter space which are not explored before, and once one go to that parameter space, the pulsars population of objects which are there will be discovered naturally. And the third is analysis technique. Say this acceleration search was not done before, when maybe 10 or 10, 15 years back, acceleration search was not attempted. And now acceleration search people are doing. Again, people have started doing this period double derivative, that is JARC search. So that means improvement in analysis technique is allowing discovery of more and more objects. Okay. So we need to, so hand in hand with the increasing the survey sensitivity, one needs to improve compute power and analysis technique. Okay, analysis technique, new analysis technique can only come up with like this 2 and 3 are interlinked. So with improved analysis technique, we need more compute power, and these can be designed only if compute power is available. Okay. Now, example for that. So you can see in this figure, x-axis is orbital period and y-axis is maximum acceleration. That means how exotic binary, in simple terms, one can aim to discover. This blue curve is for neutron star white dwarf binaries. Okay. So as you can see, for blue curve, the neutron star white dwarf binaries, this is made for considering a 2 millisecond pulsar and for different orbital period. You can see that the blue curve, in general, it's taking, if you consider up to orbital period of say 1 hour or 1.5 hour, you can say it is taking, it is having less acceleration. Okay, so to discover such objects, possibly the surveys which are ongoing or like upcoming, these could possibly discover such objects. Whereas this red curve and these green curves are for neutron star binaries and neutron star black hole binaries, and you can see that requirement of higher acceleration search, increasing the dimension, increasing the parameter space in acceleration search is warranted there. Okay. Now in this table, what we do is we list all the targeted. These are targeted surveys, and these pointed by this part. The next part of the table are the blind surveys. Okay. So we see in this table the targeted and blind surveys which are ongoing to discover millisecond pulsar. Obviously, these will, in addition to millisecond pulsar, these will discover the normal pulsars. But since millisecond pulsars are more stable clocks, as we saw in P period diagram, the period derivative is more stable. So, these surveys are targeting to discover millisecond pulsars. So what I was saying is millisecond pulsars are in some sense, people want to discover millisecond pulsars because these are more stable clock, and also these can be added, because of that it can be added in pulsar timing array, and more like precision timing can be done for these objects. Anyways, So these, as we have discussed that one point where the ongoing surveys are facing is the sensitivity limited discoveries. That means you go to higher sensitivity, higher limiting sensitivity of the survey, you will discover more and more objects. Okay, so here we see that these are the minimum sensitivities achieved from different surveys, and with time you will see that we are different telescopes are aiming to do better, like go deeper in sensitivity. Okay, and at different radio frequencies these are happening. And like this targeted survey also, blind survey also, we are seeing that different efforts are ongoing where we are trying to reach to higher sensitivity. So out of this, you can see in GMRT, we are also conducting Fermi directed targeted survey and the GMRT high resolution southern sky survey effort. Okay, so I will talk about that in later slides. Okay, so maybe here I can take a natural break. If you have any question, then I can ask. I can take that question and then proceed through the rest of the talk. Maybe.
Yes, I can see few hands up, so I can please keep the questions short and detailed questions we can take later. Abhishek Jhala, please go ahead. Abhishek, can you unmute and ask the question? Yeah.
Yes, sir. My question is related to the polarization. If we are measuring polarization along with for the pulsars, so what kind of complications will it occur in the data analysis?
Yes, so first of all, it will, the first and biggest complication is it will increase the data volume by 4 times. Right now we are recording only total intensity data, and the data rate is 48 MB per second. So one thing is the challenge of recording the polarization data, keeping the time frequency resolution same. So your time frequency resolution has to be good to achieve good sensitivity. So we want to keep the same time frequency resolution and but record the polarization data. That is possible, but that will require some kind of juggling and data managing. Now, once you record, then also you have 4 times the this thing. Data size is much more. But I will say, so here also the power of this computation will come. So if one can do that, that will be very good, because first of all, like if one can record the polarization data, then if for the newly discovered pulsar, one can do the polarization straight away. So that is one good thing. And there are many more other advantages, but the bottleneck is this, and then one need to analyze the polarization data, right? So there are also polarization calibration, etc. So these are so main bottleneck is computation, keeping the data, and yes, yeah, maybe we can go to next question. But if you are not satisfied, you can like we can talk over it.
Yeah. Okay. So let's go to the next question then. The username shows up as EP17BTech11016. So if you know who you are, please ask the question. Yeah, please go ahead.
Yes. Can you hear me?
Yes, we can.
Yes. So my question is regarding the schematic of the pipeline that you had shown, where you use some trial DMs to redisperse the data. So my question is, how do you select those DMs? Do you look at any nearby pulsars as to whether region at which you're observing, or do you just use, like, do you have a pre-known data set of DMs which you use as trials, or is there like an intelligent way to just guess the DMs so we are closer to the actual value or something like that?
Yes, so what you said is a good question, but the thing is, you will know the DM if you have, say, if we are targeting a globular cluster, so then we know a nearby DM value. Okay, so then we can search for that around that DM. But in general, we do not have any information on the pulsars that we are searching for. Okay, so these are completely blind searches. So there you do not have any intelligent information on DM. So there the DM steps needs to be decided. First of all, we know Generally we search from, say, if we are not searching for first radio burst, Shears will tell more about that. So if we are searching only for pulsar, generally we limit our search for up to 1000 dm or 500 dm per 500 per cc as dm value. Okay, so then we are limiting that. Then we have to grid, make the dm trials and make the dm grids. Right. So that will depend on how much. So you have, when you are observing your observing bandwidth, you will have, say, 200 megahertz bandwidth, you make 4096 frequency channels. So there is finite observing bandwidth. Within that, there will be some smearing. So you will not make a DM step finer than the DM smearing within that channel. So for that, we generally use it. So there is a pulsar searching. This pulsar searching pipeline is based on this Presto software written by Scott Ransom. So there we have a utility called ddplan. You may look at that Presto web page and look at this ddplan software. So what it does, it takes all these things into account when one user gives these inputs and makes a ddplan which is perfect for your survey. Yes. Yeah.
Okay,
Maybe
thank
you can.
you.
Yeah.
Yeah, shall we take a couple of more, Bhaswati?
Yeah, maybe.
Maybe one.
Yeah, one
Two.
or two.
Yeah, okay. Adrija Panigrahi, please go ahead.
Hello, ma'am. Am I audible?
Yes.
Yes.
Ma'am, in the slides you showed at the beginning, there was a slide where you showed where you talked about the average, about taking the average of the pulses. Ma'am, there was a plot where there were shorter peaks, dense shorter peaks, and there were sharp peaks in between them. Ma'am, are those shorter peaks do they correspond to the noise or something else?
Okay, so I think what you are, just 1 minute, though it will take some. Yeah, so you mean this figure, right? So these are structures in the average profile, Adrija.
Yes,
okay?
ma'am.
So and different pulsars may have different structures in the average profile, and this mostly because of the line of sight geometry. This alpha beta values, you will have different kinds of average profile observed from different pulsars. Okay. Yes.
Okay, ma'am. Thank you.
We can take next question.
Okay, no, I don't see any hands up. So Bhaswati, please carry on. Yeah.
I will then carry on. Okay, fine. So now we have discussed up to this, and then I will talk about the blind and targeted surveys in which I am involved with the GMRT. Now the first question is, why GMRT? So GMRT is a giant meter wave radio telescope. You know about that, and you can also read up more on that. And then you have it has very large collecting area, and it operates at 4 different wave bands. And then since pulsars have very steep spectra, low frequency searches are better for finding out weaker pulsars. And we can have 2 kinds of beam. One is we can combine the antenna signals in incoherent and phased array, and which are incoherent array having the wider beam is more suitable for pulsar searches, where the coherent array is not. But simultaneously you can also record with incoherent array coherent array data and do more sensitive pulsar searches, and you can reach to very high sensitivity, which is compatible to the surveys that have been done with the very largest with other very sensitive facilities like Meerkat and all, and GBT and PARCS with this telescope. Now, as I have said already, so pulsar surveys could be targeted towards a given direction, or it could be blind survey. Okay, so targeted survey have discovered with GMRT has discovered some pulsars over the time, and blind surveys also. And I will mostly talk about the Fermi directed targeted survey that we are doing, and the GMRT high resolution southern sky survey that we are doing with the GMRT. So Fermi directed targeted survey, what we do is we have the Fermi gamma ray telescope is scanning the sky at some date, and from that scan we have a list of unassociated point sources. That means these point sources are not associated with any known source class. And on those point sources, we point our telescope and try to find out pulsars. So this is being coordinated between all these observatories so that there is no repeat of observing sources. And we with these Fermi directed sources, you see this red part is the observation. Is the millisecond pulsar that has been discovered with the Fermi directed survey. So you can see with the Fermi directed survey, the number of millisecond pulsars discovered has been increased by a lot. Okay, so we have started Fermi directed survey with first in 2011 when only 32 megahertz bandwidth observing was available with the GMRT, and we have discovered 7 millisecond pulsars with that, and the details are there. Right now, I'm not going into that. So these are the pulse profiles of these black lines. So I should first say this green and the blue lines are from the GMRT observations at 2 different frequencies, 322 and 610 megahertz. Whereas after discovering the pulsars with the GMRT, what we do is we give our parameters, which is arrived at after long-term timing observations of the pulsar. So with long-term timing, we know this pulsar system better, and we can generate a parameter file, and we give that. What we do is we give that parameter file for holding the Fermi gamma ray photons. With that, then we have discovered this Fermi the gamma ray pulsation from these pulsars, which is denoted by this black line. And this pulsar, this 1536 minus 4948, is a very strong gamma ray pulsar. And so here the efficiency of gamma ray emission is very high, and it has proven to be also like good for limiting the gamma the gravitational wave background with the Fermi-Lat data. Okay. Anyways, so in addition to these, we have also discovered during the Fermi directed survey, we have discovered some of the pulsars which are not associated with the target point source. Okay, so probably with deep searches, we are able to discover these MSPs which were would not have been discovered by these 10-minute pointings. Okay. Fine. And now the phase 2 of Fermi directed survey that we have started with the GMRT, where we are investing 200 megahertz bandwidth, and we are searching for the sources, and we think that we will be discovering more and more MSPs through that, because we have found that there is no, so basically what we are targeting now are relatively weaker gamma ray sources, but we have found that there is no correlation between gamma ray luminosity and the radio. So that's why like strong radio pulsar radio MSP can be there while at the position of weak gamma ray sources. Okay. Fine. So this plot shows that all the 8 MSPs, 7 are for Fermi directed. This highlighted one is a transitional millisecond pulsar, which is I would say the most interesting pulsar discovered with the GMRT, which is transitioning from radio millisecond pulsar to accreting low mass accreting binary system. So it has been caught in the place of transition. So it was there as accreting binary, and then we have discovered it in this radio MSP state. Probably it will change its state again. Okay. So I'll not get into the science result more, but the references are there. You can go to that if you want. So now coming into the blind survey, the GMRT High Resolution Southern Sky Survey. This is the survey, since we do not know the a priori information of most of the pulsars that are existing, we have to do blind surveys. Okay, so this was the survey again started with the 32 megahertz legacy GMRT system, and it has discovered 27 pulsars till now. And out of these, 14 pulsars are, so though it was started earlier, a second phase of this, phase 2 is running with the upgrade GMRT system with 200 megahertz bandwidth, and we have discovered 14 discoveries. We have 14 discoveries with the UGMRT survey, and this includes the first millisecond pulsar discovered from UGMRT and first rotating radio transient that has been discovered from the GMRT. Okay, so this plot shows the the discoveries that has been made with the GHRSS survey of different kinds of pulsating sources. Okay, and you can also visit the GHRSS web page to see the updated details of this. Okay, so this shows the parameter space for phase 1 and the phase 2 of the survey, and you see that compute cost is quite a lot, considering which parameter space you will consider for acceleration search and all. Okay, so this table shows the discoveries through the GHRSS survey, and what I want to point out is most of the pulsars that we are discovering are relatively weak. Okay, and 25% are less than 1 millijansky. So with these such sensitive surveys, which were not there in the southern sky before, we are able to probe a population of the pulsars which are very weak, and probably that will give us some idea about the like luminosity distribution of the existing sources, and also like more and more discoveries will tell us how the distribution is. Okay, so these are profiles of the GMRT discoveries. Like Adriya said, here also you can see different kinds of shapes. So this is like pulsating sources. It could be on and off like this profile, or it may have structures depending on how your line of sight is cutting it and whether the emitting regions in which pattern they are distributed. Okay, so some features of this GHRSS survey which is relevant for this discussion forum is, one is very high resolution observation. So we do our time sampling is at 81 microsecond and high frequency resolution observation, and that is needed to reach to the sensitivity limit that we are reaching. And obviously the RFI is a very big contributor to reduce our sensitivity or reduce our discovery potential. So we need to take care of the RFI. So we have different means through which we are trying, and this is in process. In addition to that, machine learning, as I have said, the number of candidates generated is it is impossible to look at the candidates by human eye. And so you need help from machine, and after that you can, after a machine screens the candidate, you can do that. But for that you need to train the machine efficiently, in which we are in the process of doing that, and some students are involved in that. Okay, so if I think of how we are, say if I consider this GHRSS survey, then how from the GHRSS survey phase 1 to phase 2 we are moving, and what that means in the SK Pulsar Search scenario. So in GHRSS phase 1, we attempted a if you consider the radiometer equation, our limiting sensitivity was 0.5 millijansky for a 5 sigma detection. So if a pulsar had 5 sigma 0.5 millijansky as the flux density, then we will detect it at 5 sigma, considering reasonable RFI condition. Okay, so which is made like it increased, the discovery potential is increased with when the bandwidth has increased from GHRSS 1 to GHRSS 2 by 200 megahertz. Now we have 0.3 millijansky limiting sensitivity, and again when we will have SK1 in online, then we will be even more sensitive. Okay, so these plots show with the comparison of the Fermi directed survey and the GHRSS survey with the existing surveys by GBT, which is GBNCC survey, and PARCS, which is HITRAN survey. And we see that we are at the same ballpark or better in the performance. Okay, so now the GHRSS survey, the discovery rate, if we compare, now you can say, okay, how many pulsars you have discovered, whether that is as expected. Okay, so if we compare the discovery rate, we see that the discovery rate wise, it is one of the highest pulsar per square degree discovery rate. Now I will go to the last topic, which is relevance of HPC in future pulsar searches. Okay, so now as we talked about the design of the telescope, so we need large number of small telescopes will lead to the future sensitive telescope, which can discover very faint pulsars, which are lying. This 95%, maybe some fraction of that are very faint pulsars. So we need that. And Recording raw voltages from the antenna and possibly forming phased array beams will allow improved sensitivity, but that needs improved computing. Again, we have data volume, very high data volume, 48 MB per second we record. So in 1 hour, around 200 GB data. And so for handling that and say like transferring that to the HPC facility, so for that we need very high performance like data transfer links, high performance computing, etc. And then searching for enhanced parameter space. So your parameter space also decides your discovery potential. So if you want to optimize your discovery potential, your parameter, you have to put in enough compute power so that you discover the exotic objects, because these all these say neutrons or neutron star binary or neutron star black hole binary are expected to have very high acceleration and maybe higher derivative of the period. So for that you need to search for, you need to increase your search parameter space. Again, probing luminosity distribution also another thing. So with higher computing facility, when one will discover fainter pulsars, fainter millisecond pulsar, then intrinsic luminosity distribution will be known. Otherwise, maybe the distribution that we are considering is biased. Okay. Now, again, I am coming back to the same plot. If we consider the SK based, or maybe not even SK, maybe futuristic searches, then as you can see, in y-axis, as much maximum acceleration value you can allow, you can expect to discover these exotic systems like neutron star binaries or neutron star black hole binaries. Okay, so for that you need to scale up the compute power that you are using. So if I consider that I am going to 350 meter per second square, like this blue scaled region, then I can expect that I will be discovering some of these exotic objects. Whereas right now what we are doing is we are going to 5 meter per second square or sometimes 20 meter per second square acceleration as the acceleration trial value. Okay, so up to that value. So we cannot expect to see these kind of exotic systems. So we need to scale up our compute power. Okay, so the as we see that with, so, and I should say that this is the aim that is made for SK1. Okay. And also with the SK, we aim to discover, so many more pulsars will be discovered in different stages of SK. So this is a PSR copy, is a open software. One you can also download and try out, and that can be done in your usual desktop computer. And from that, what you can do is you can predict the population of pulsar that will be discovered with different surveys if you give the survey specification. So this has been discovered by Duncan Lorimer and the group. So we have tried that for our GHS survey and all other surveys, and Lena and myself have tried that for SK1, and this is the population. So we can see around 9,000 new pulsars and maybe 1,200 new MSPs are expected from SK. Now, if we go beyond that, so more compute power if you put in, like after acceleration, if you put in the JAG search, here you see this part is with, so if you search for a pulsar, this black line means you have discovered a pulsar, and it is tilting means the period is not stable. Okay, so the period was correct here, but not correct here. So that's why you are getting these curved lines. Okay, so your aim will be to make these lines straight. So for that, what you need to add in more and more derivatives of period. So first of all, this is only period search. You see this kind of curvature. Now, once you put in the acceleration search, you see this is improved and your detection significance will be better. Now, if you put a second derivative of period, that is JAG search, then it is almost straight, though you see that it is not fully. So with the JAG search, you expect to detect more weaker such MSPs which are in exotic orbits, but the compute requirement will be much more. Okay, so I think I will summarize now, which is in this talk I have tried to give you an overview of the compute requirement for the pulsar searching and the details of pulsar searching. And since we are nearest to the GMRT telescope, some efforts with the GMRT is discussed. And finally, what I want to emphasize is improved discovery rate and very interesting discoveries can be expected with the ongoing surveys if the available compute resources can be enhanced and also like usage can be more easier. Yeah, I will stop here for questions. Thank you.
Thank you, Bhaswati, for so many interesting results and also talking about the basics of Pulsar Search. So let's take some questions. So Abhishek Jhala, please go ahead.
Thank you, ma'am, for such a wonderful talk. My question is related to the Pulsar backend. Can you please give me in summary what is the difference between Pulsar backend system and the FRB backend system?
Okay, so you want to know about how the Pulsar searches are done and how the FRB searches are done, right?
Yes, ma'am.
Okay, so observation wise, since you mentioned backend we will, so this is a very interesting question and good question. Probably with the next talk by Sriharsh, things will be much more clearer to you. But at this point, what I will say is, so you have seen that the Pulsar searching have 3 steps. One is this search for the dispersion, so at different trial DMs, right? And the next step is search for periodicity and periodicity derivative, right? So this search for dispersion measure part will be common for pulsars and FRBs also, right? Because for FRBs also, FRBs are though at much higher dispersion values, but they have that will be common, right? Though for FRB search, as you have seen that the FRBs are extragalactic, and so you will need to increase your parameter space. Okay, but as of now, periodicity is not like, at least short-term periodicities like Pulsar is not established for FRBs. So periodicity search and acceleration search is not relevant there, right, Abhishek? So what you need for FRBs is dispersion search, and then the single pulse looking at efficient dispersion search, and then looking at a single events, right? Yes. Does that answer your question?
Yes, ma'am.
Okay, Rohit Nayak.
Yes, ma'am. Yes, sir.
Yes.
I have a question. Can you explain the pulsating rate of a single pulsar and of pulsars in a binary pair? Are there any differences?
Okay, so if you consider the pulsating rate, that you can find, so each rotation of the pulsar will give you a pulse, right? So
Yes.
The moment you are recording 2 rotation from a pulsar, you can find out the pulsar period.
Okay.
Categorically. But though there are some things like when we discover the pulsar, sometimes it happens that we discover a harmonic of the pulsar. That means instead of P, I am assigning the pulsar a periodicity 2P.
Okay.
So for that we have to fold that pulsar data at P, 2P, 3P, and P by 2, 3P by 2, and ensure that whether the periodicity at which I have discovered it is the correct periodicity. But leaving that aside, coming to your question, each pulsar have its characteristic period, right? So you have you can get that periodicity. So do you have any? So you want to know what the periodicity is? Yeah, sorry, you tell me.
I have one more question.
No, but this question is sorted. This question is.
Yes.
Okay, yeah.
Ma'am, that dispersion measure value is only calculated for pulsars and FRBs or for any other astronomical objects?
Dispersion measure, if you categorically say, dispersion measure can be there for any object, right? If you have the position of that object and there is some distance between that object from you to, so if you look at the definition of the dispersion measure, that is integration of any DL. So that does not say that whether I'm talking of pulsar, FRB, or source XYZ.
Okay. Thank you.
Shumit Banerjee, please go ahead.
Thank you, sir. Good afternoon, ma'am.
Good afternoon.
Ma'am, I have 2 questions for you. Number one is, there is a statistic you mentioned in your talk that 95% of the pulsars are not discovered yet.
Yes.
My question to you would be, what kind of a statistic do you use to figure out these numbers? That is the first question.
Yeah.
The second question is, if you could explain how are the millisecond pulsars related to gravity wave? That will be the second question to you.
Okay, so let me first answer your first question. So this is a very good question. I am talking about 95% are not known. How these are, how do one knows these numbers? So this is not, these I don't, like, we will not say that we know statistically, but this we will say we will know from some population models. So how population models that predict how the pulsars are generated. Okay, so basically, I am not an expert on that. What I look at is the work by other researchers who have studied the population model. I am not sure whether I have given the reference, but maybe you can find out or write to me. Who have found out that, like with the genesis of the pulsar, what should be the rate of what should be the total number of the pulsar that one expects now. Okay, now. One thing could be that, like, your observational study may give some input to modify that that population model, and another thing could be like you are not discovering those objects, like those lot of objects, because your discoveries are sensitivity limited, and we have lot of clue for that. For example, the 3 pulsars that I have said, the 3 pulsars we have discovered from Fermi-directed survey were not associated to the Fermi gamma ray point sources. That means that gives some indication, like we have looked at 375 sources. Out of that, we have found 4 sources which are associated to the target pointings and 3 not. Okay, so that says that the importance of very deep and blind surveys. Okay, so that means with which are like generally for doing that you have to invest lot of telescope time. So these are not done as of now very frequently. But with that, possibly one. Yes, does that answer your first part of your question?
Yes, and that does. One follow-up question, if I may, on
Yes.
the population model.
Yes.
So the population models, we do get the number of the pulsars. Are these direction sensitive? And do they give us at what direction are we more likely to find certain pulsars than others?
No, these are not that much. It will not tell you. Yeah, that's a very good point. If one knows that, then one can point your telescope to that direction, but not generally. But generally, you will know that maybe in the galactic plane or near to the galactic plane, there could be more pulsars, but at the same time, since the sky temperature is high on that direction, your sensitivity will be low, and at low frequency searches, you will get dispersed pulses, so detection will be hampered by that. So generally, when we search, as of now, we are targeting, say, above some galactic latitude region. Okay, but it is true that there are also searches in the galactic plane. Okay, so maybe you can look at this PSR copy software, which does populate the this thing with different ranges. So this you can like download in your computer and make it run. And you can, when you are giving survey inputs, you can give defined ranges and see what is the. Okay.
Okay, let's move on to the next question. Deepanjan, please go ahead.
Hi, Bhaswati. Very nice results. I have missed a few bits of your talk, so apologies if my questions are repetitive. I had two questions. One is I saw in the list that the highest pulsar you had from this GRHS survey was 757. So is that the record holder now for the fastest spinning pulsar?
No. Oh, wow, what you were saying?
So the fastest spinning pulsar in your survey.
Yeah.
I saw in the list something like 757 hertz.
Yes, 757 milliseconds.
Is that the highest now?
No, not at all.
Okay.
Yeah, so right now the highest spinning pulsar is 1.4 millisecond or so,
Okay.
But we have discovered 2 millisecond pulses from GHRS's survey, which is this 5 millisecond one, and so these ones. So these are relatively higher spin pulses.
No, I mistook this slide. I actually thought it's hertz, not milliseconds. So I read it other way around.
Yes.
My other question is, since you are discovering very low luminosity pulsars right now, and are you pushing towards the deadline? And if so, can you elaborate of what physics might be learned from that?
Yeah, that is a very interesting question. Actually, very recently, Shubham has discovered one pulsar, which is very it has the lowest duty cycle known till now, and possibly we'll be doing that. But so first thing is, like, when we discover the pulsar, we have not so after discovery it takes a while to time the pulsar and know the p dot value. So we cannot right away place it in that pp dot diagram, but it seems to be nearer to the deadline.
Okay, but you haven't found anyone that has crossed it yet?
No.
Okay, thanks.
Yeah.
Okay, one final question. Shiv Prakash Mishra, please go ahead. To unmute yourself and ask the question.
Yes, sir. So, ma'am, actually, I did a project in my MSc. So, on that project, I have done the machine learning algorithm for RRLI research. So, on that, we use the dataset of the SDSS. So, on this, they have color indexes. Based on that, we have classified the RRLI array. But here in the pulsars, I think you have to use the time series analysis. So how could you because I want to do the one of the supervised learning based on passive learning means active learning. Active learning. So I want to use the time series and the FITS photographs so that I can classify different galaxies and other things. So can you some light on that?
So if you want to know about existing machine learning algorithms for the pulsar, so these are available in GitHub. You can take from there. So I can point you towards a code by Rob Lyon. So you can search by his name. So this is the machine learning classifier that we use for GHRS survey. So that is available in GitHub, and you can load that and look at the features. And there is another classifier by called PIX classifier that also you can look at. And the third one is the SPIN, SPIN. Okay, so these three classifiers are the existing one, but people are writing the new ones. And basically,
these are based on, ma'am, these are based on deep learning or just machine learning?
Some of these some of these are based on, so it varies. So you have to go through which one you are. So like this Rob's classifier is so it is based on Python and then Java code. Okay. So you can, this will be varied, and you can look at this. And also in TensorFlow, we are finding right now that one can easily write your own machine learning code. So that also, if suits for your application, you can do that.
Okay, thank you.
So basically, we take some features and from the diagnostic plots that we make, the pulse phase versus time, or the pulse phase versus frequency, and then train the machine to learn that. Okay. Yeah.
Okay.
Yeah.
That's nice. Yeah. So